Welcome, everyone, to today's Explainer. I'm absolutely thrilled to guide you through this today because, honestly, we're tackling one of the most fascinating engineering triumphs of our era. We're going to demystify the incredible tech behind self-driving cars. So let's just dive right in. For decades, autonomous driving was basically just science fiction. But today, the advanced driver assistance systems, or ADAS, embedded in our cars are completely transforming how we commute, pushing us closer and closer to full autonomy. But how exactly do they pull this off?
Think about this for a second. How does a massive, multi-ton machine flying down the highway at 60 miles per hour safely navigate unpredictable, totally chaotic city streets without a human touching the wheel? How does it know the difference between, say, a plastic bag blowing across the road and a child chasing a ball? It's an incredibly high-stakes environment. The contrast between the sheer chaos of the real world and what the machine has to do is immense. Literally, one wrong move can be catastrophic.
To truly grasp how this complex system operates, we've got a clear roadmap for today. First, we'll look at the anatomy of autonomy, then break down the car's artificial senses. After that, we'll explore why single sensors fail, uncover the true power of sensor fusion, and finally, map out how this all moves from perception to action. All right, Section 1, the anatomy of autonomy. To wrap our heads around this complex hardware, it actually helps to just compare a car's architecture to our own human biology. Notice how clearly this biological workflow maps to a technical pipeline. Over on the far left, we've got our eyes, the sensors, like cameras, radar, LiDAR, and GPS. They feed raw data right into the brain's perception block. That block's job is to detect lanes, traffic lights, signs, open space, and also localize the car on a map. From there, the data flows into the planning stage. This is where the behavioral forethought kicks in, stuff like route planning, predicting what other objects are going to do, and mapping out a safe trajectory. Finally, that decision gets handed over to the control block on the right, which triggers the actuators. Think of those as the muscles, using advanced steering and braking algorithms to physically move the car. Moving on to Section 2, the car's artificial senses. Let's zoom in on that very first step of the pipeline, because the data going into the processor is really only as good as the sensors collecting it. So automotive sensors generally fall into two distinct camps, active and passive. Understanding the difference here is absolutely crucial. Active sensors act kind of like a bat using echolocation. They actively shoot out wave energy, like radio waves for radar or light pulses for LiDAR, and then they measure the energy that bounces back off obstacles. Passive sensors, on the flip side, don't shoot out anything. They just sit back and take in existing environmental info, like visual light or thermal heat. Your standard digital camera or an infrared camera, perfect examples of passive sensors. Let's break down a few of the heavy hitters. First up, cameras. These are basically the driver's vision. They're absolutely essential for complex, detail-heavy tasks, like telling a road from a sidewalk, reading speed limit signs, or spotting a pedestrian. Then we have IMUs, or inertial measurement units. These are vital because they measure the physical orientation of the car, the yaw, pitch, and roll. Imagine hitting a steep mountain road or a patch of black ice where the tires lose traction. The IMU tells the brain exactly how the car's physical posture is shifting in real time. And of course, GPS, which pinpoints the vehicle's exact global location. Every single one of these gives us a unique, highly specialized piece of the puzzle. Which brings us to Section 3, why single sensors fail. And folks, this is where we hit a massive engineering hurdle, the fatal limitation of relying on just one artificial sense. Look, the real world is messy, right? It's not a clean, perfectly lit lab. Think about driving into a sudden pea-soup-thick patch of fog or getting a massive splash of mud across your windshield. A passive camera is instantly blinded. Or what happens when you drive into a long underground tunnel? Your GPS instantly drops. And those active range sensors like radar, they can easily miss hidden objects if a bigger vehicle is blocking the beam's path. If an autonomous system relies on just one type of sensor, a simple change in the weather could literally be lethal. The source material for today's explainer puts this pretty starkly. To quote it directly, sensors may fail in detecting hidden objects. GPS-based approaches failed to precisely localize in tunnels. It goes on to explicitly state that the vehicle absolutely must recognize its environment without human interaction, no matter the conditions. Basically, lacking redundancy is a recipe for disaster. We just can't build a safe system if a little bit of mud or a dark tunnel shuts the whole thing down. That brings us to Section 4, the power of sensor fusion. This right here is the technological hero of our explainer. It's the breakthrough that turns vulnerable individual sensors into a super-powered, overlapping web of awareness. By definition, sensor fusion is the integration of two or more diverse sensors to improve accuracy, provide redundancy, and sense the environment safely. I really want to hammer home that word redundancy. By layering different tech together, taking the visual detail of a camera, the distance-measuring power of LiDAR, and the weather-piercing radio waves of radar, the vehicle covers the blind spots of any single device. If the camera is blinded by glare from the setting sun, the radar doesn't care. It still sees the car braking ahead of you.
And it's brilliant to see this concept in action. Notice how the safety zones literally overlap around the car. The dark blue zone shows the long-range radar reaching way out ahead for adaptive cruise control. Layered right on top of that, you've got the gray LiDAR and the green camera fields handling pedestrian detection and traffic signals. Around the sides, there's shorter-range radar for blind spots, and those red ultrasound bubbles right up against the bumpers for precise parking assistance. It's a comprehensive 360-degree overlapping map of safety. There's no single point of failure here.
Section 5, from perception to action. Okay, so the car now has this seamlessly fused picture of the world, but what does it actually do with it? Let's step inside the brain of the vehicle for a second. It's not enough to just see a chaotic scene full of cars, trucks, and pedestrians. The system has to actively make sense of it. First, it detects the objects, placing those little colorful bounding boxes around the cars, the cyclist, the pedestrians. But it doesn't stop there. Then it moves to object tracking, monitoring how these objects move, frame by frame over time. Why? Because of the final piece, trajectory prediction. By tracking a cyclist's speed and direction, the car's algorithms can mathematically predict exactly where that person will be 3 seconds from now. It's planning for the future, not just reacting to the present.
Ultimately, this wildly complex process boils down to 4 distinct steps for navigating traffic. Step 1 is perception and prediction, gathering all those integrated sensor readings to know where things are and where they're headed. Step 2 is behavioral forethought, translating those insights to figure out a safe maneuver. Step 3 is trajectory planning, analyzing the absolute best path based on safety, comfort, and efficiency to create a precise driving line. And finally, step 4 is controlling, sending that final decision to the actuators to actually steer, accelerate, or hit the brakes. We've seen how the anatomy of autonomy works today, right? From the basic biological metaphor of eyes and brains, all the way to the advanced redundancy of sensor fusion, overlapping those safety zones. As humans, we only have 2 eyes. We get tired, we get distracted, and our physical reaction times are limited. But through sensor fusion, a machine maintains a constant 360-degree view that never blinks, never checks a text message, and never gets sleepy. So I want to leave you with this final provocative thought. If sensor fusion gives cars a flawless 360-degree view that never blinks or gets distracted, will there soon come a day when we trust the machine's senses more than our own? Thank you so much for joining me on this explainer, and keep questioning the world around you.